Hello and welcome to this episode of the Industrial Engineering Notebook. Today's topic is defining stress. This is not the feeling that you get before an exam. This is the unit of measure we use in continuum mechanics. The idea here being if you have something with a kind of crazy shape, doesn't really matter what shape it is, maybe this is a widget of some sort, and you know the external forces, you know that there are a few external forces acting on it, maybe a pulling force right there. But sometimes you need to get down into the nitty-gritty and figure out, okay, at this point, what are the forces right there? And that's when you're going to need more advanced tools than statics gave us. Go check out the statics videos for more details on that. Let's say we've got a block and it's being pushed up against this wall back there. So we might represent that with a force vector right here. But that is a simplification. So I've drawn an identical block over here. And the reality is, if you're pushing, maybe let's say you're using your hand to push the block against the wall, there's the cross-sectional area of your hand right there. And as you push it against the wall, you're not just applying a single force vector. Each little point on your hand is applying a little force vector. And there are a lot of points on your hand, so you can't even really see the hand anymore, but it's all right there. All those little itty-bitty vectors that add up to this big vector that we were using in statics. And in continuum mechanics, we can't use this simplification anymore, and I'll show you why. Let's say you got a cylinder that looks like this, which would simplify to, let's say, a 500 Newton force. The reality is, there's another way to get to that 500 Newton force. And that would be if you have a larger cross-sectional area and just smaller forces at each point. So both of these cylinders here, even though they're shaped differently, are experiencing 500 Newton forces. But we know intuitively that this cylinder is going to break or bend or whatever first. Why? Because each molecule is experiencing a larger force vector, even though they all add up to 500 newtons in the end. These poor points on this cylinder are experiencing way more force than the points on the cross-section of this cylinder. So we need a way to account for this. That's why force isn't enough when we're dealing with continuum mechanics. So instead we use force per area. And force per area would account for this difference. Because each point is experiencing a lot more force on this cylinder, it would have a high force per area. And because each little point on this cylinder is experiencing a very small amount of force, it would have a low force per area. Which means that force isn't really a good measure on its own to determine when something is going to bend or break. Really what you need is force per area, which is also called stress. And stress comes in two flavors. There's normal stress, like we just saw. And normal here doesn't mean like your average stress. It just means stress where the force is at a 90-degree angle to the cross-sectional area. So all these little force vectors are at 90-degree angles to this cross-sectional area here. The other flavor we haven't seen yet. And it's called shear stress. That's what it looks like. And it is just stress where the force is at a 0-degree angle to the cross-sectional area. So this is kind of like in statics how we had forces in the y direction and forces in the x direction. But in continuum mechanics, we're not concerned about x and y direction as much as we're concerned about stresses acting normal to the surface that you're concerned with and stresses that are at the same direction as the surface you're concerned with. Normal is just another way to say at a 90-degree angle to or perpendicular to. Normal stress is often denoted with a lowercase sigma, the Greek letter sigma, lowercase, and it is just normal force divided by area. Shear stress is denoted by the Greek letter tau, and it is just the shear force or the force at a 0-degree angle to the area divided by area. So both of these are force divided by area. We just use different Greek letters to represent them depending on the direction. Stress, like pressure, is often denoted in newtons per meter squared, which is the same as a Pascal. So these are the units in the metric system that you might see. And now you're prepared. If you get a 3D object, maybe you know a couple of the external forces and you're wondering what kind of stress, what kind of forces are being experienced at this point right there in the object, there are equations that you can use that build on normal and shear stress, figure out exactly what kind of forces are being experienced at that point, or this point, or whatever point. And continuum mechanics is actually one of the sneakiest topics in industrial engineering because in the manufacturing process, you need to be able to tell what is and is not important and what decisions will and will not help your process. So a simple application of normal and shear stress would honestly just be screws and nails. Screws are good at high normal stress points. So if you pick your point and there's a lot of normal stress there and you need to add some sort of attachment, a screw would be your go-to. Nails, on the other hand, are good at high shear stress scenarios. So if you pick your point and there's a lot of shear stress there and you need to add an attachment, go for a nail. And this is just one of the many applications where this is good to know in manufacturing. So much of manufacturing is just taking a raw material and turning it into a product. And that often means reassembling, breaking, bending, attaching things, which you can only do effectively if you have a good understanding of what kind of forces your widget is experiencing at each little point. If you liked this video, I recommend hitting that like button. And if you want to see more videos like this, you should subscribe. That will tell me to, hey, keep making more videos like this. And if you have questions, please put them in the comments.